Dear students, I am Mahesh Javalkar of Maratha Mandal Polytechnic, and today I am posting my ninth video on DCET questions on the subject BEEE, that is Basic Electrical and Electronics Engineering. So let's start with the first question. Question number 161. The average EMF, that is electromotive force, induced per turn in a transformer is given by which expression? So the expression what we get after the derivation is 4F, that is 4 into frequency into phi m, that is maximum flux at the quarter half cycle. Okay, so 4F phi m. Now if you want to prove that, you can say this EMF equation of transformer. Suppose N1 is the number of turns of primary coil and N2 is the number of turns of secondary coil, and phi m is the maximum flux in core, which is also equal to a magnetic strength into area, B into A. Then F is equal to frequency of alternating current. Then if you see the figure of the waveform here, the waveform will increase initially and it will reach the maximum flux phi m when it is quarter half cycle. Quarter half cycle means 1 upon 4 f second. Okay, so average rate of change of flux will be phi m upon 1 upon 4 f. That is equal to 4 f phi m Webers per second or volt. Now the rate of change of flux per turn means average EMF per turn, that is equal to 4 into frequency f into maximum flux phi m volts. So 4f phi m should be the answer here. So option C is the right answer. The average EMF induced per turn in a transformer is given as 4 into frequency into maximum flux. Okay, that is 4f phi m. Okay, then we'll go to the next question. Question number 162. The EMF equation of the transformer is, okay, so as we have seen in the first expression, it is 4f, okay, into number of turns into the maximum flux. If you want to speak about primary and secondary, then E1 will be for primary and E2 will be for secondary. N1 will be the turns of primary and N2 will be the turns of secondary. Now, if you observe the first equation here, the first equation says E1 is equal to 4.44 exactly F into N1, that is number of turns of primary, into phi m, and E2 is equal to 4.FF N2, that is number of turns of secondary, into phi m. Okay, so option A is what you have done as E1 is equal to 4.44 F into N into phi m. Okay, so this is a general statement. If it is E1, then this is N1. Okay, now in this case, if you convert phi m, that is flux, maximum flux, into magnetic field strength into area, okay, so B into A, then you will get E1 as 4.44 Fn B into A. Okay, so this is N1. That is what is shown in equation 2. Similarly, in the first equation, if you convert frequency as 1 by T, then you will get E1 is equal to 4.44, okay, 1 by T N1, okay, phi m. This is what is shown in equation 3. Okay, so that means all the above equations are correct. So if you want an explanation for this, we can take the basic equation of the transformer. Okay, so option 1, we are having E1 is equal to 4.44 into F N1 phi m, and E2 is equal to 4.44 F frequency N2, that is secondary turns into maximum flux phi m. Then first put the value of phi m as B into A. Okay, so that is your magnetic strength into area. So the equation becomes, in option 2, whatever is given, that equation comes into picture. And now in the same first equation, if you put frequency F is equal to 1 by T, then you will get the equation in option 3. That means all the first three equations are correct. So all of the above are correct here. Okay. Then we'll go to the next question. For maximum efficiency in a transformer, okay, which of the following statement should be there? So core losses is equal to 2 into a copper losses, or a core losses is equal to copper losses upon 2, or a core losses is equal to a copper losses, or core losses is equal to copper losses upon 4. Okay. Now in this case, the third statement, that is core losses is equal to a copper losses, will be the right answer, because if iron losses are equal to the copper losses, then only the maximum efficiency will be coming out of a transformer. So for maximum efficiency, your iron losses or the core losses should be equal to copper losses. So option C is the right answer over here. Then we'll go to the next question. Question number 164. An alternator is also called. Okay. Now, basically, an alternator is a machine which will convert mechanical energy into a alternating electrical energy, alternating electrical quantity, AC. Okay. So it is a generator and it is also called as synchronous generator. Okay. So an alternator is also called as synchronous generator. Option A will be the right answer here. Then we'll go to the next question. Alternators are rated in what unit? Whether it is a kilowatt or kilovolt ampere or resistance, or kilovolt ampere or horsepower. Okay. So option C is the right answer over here. It is kilovolt ampere. So alternators are rated in kilovolt ampere, kVA. Okay. Then we'll go to the next question. Question number 166. A machine without a commutator providing an AC EMF to the external circuit is called as, okay, obviously a machine which converts mechanical energy into electrical energy, that too as AC quantity, alternating quantity. It is called as alternator. So here option B is the right answer. B is alternator. Okay. So alternator is a machine without a commutator providing an AC EMF to the external circuit. Okay. Then we'll go to the next question. Question number 167. The basic operation of an induction motor, that is AC motor, is based on what? Okay. So here the stator and rotor. Okay. Stator is a stationary part and rotor is a rotating part. Okay. So the magnetic field of stator will induce a current in the rotor, which will induce its own magnetic field, and both the magnetic field will interact with each other and rotor will start rotating. That is the basic operation. So that operation is happening because two magnetic fields are interacting with each other. So it is a case of mutual induction. So here B, mutual induction, will be the right answer over here. The basic operation of an induction motor is based on mutual induction, because in a magnetic field you are putting a conductor which can rotate, because current will start flowing through it, alternating current will start flowing through it, and that will produce a magnetic field that will interact with the original magnetic field, and rotor will start rotating. So it is a basic case of mutual induction. Okay. Then we'll go to the next question. Question number 168. A universal motor is one. So here options are: which can run on any value of supply voltage, which has infinitely varying speed, which can operate on AC as well as DC voltage, which can work as single phase or three phase motor. So it is very basic. If a motor works on AC and DC both, if a motor works on AC and DC both, then it is called as universal motor. So option C will be the right answer here. A universal motor is one which can operate on AC as well as DC voltage. So option C is the answer, that this motor will operate on AC and also on DC. Clear? Then we'll go to the next question. Question number 169. It says that how many steps are involved in the construction of single phase induction motor? Okay. So the main steps involved in the construction of single phase induction motor are five. And which are those five are? They are stator, the stationary part, the stator windings of the stator, then rotor, the rotary part, then starting switches and electrolytic capacitor. So stator windings, rotor, starting switches, and electrolytic capacitor are the five steps which are required in the construction of single phase induction motor. So answer should be five over here. Then we'll go to the next question, question number 170. What will happen if DC shunt motor is connected across AC supply? Okay. Now, if a DC shunt motor is connected across AC supply, okay, then it will oppose that and there will be a more resistance to it. Okay, because coil will oppose your AC here. So AC will be opposed and it will produce more reactance, so more resistance to the flow of current. Due to this, there will be heat, and due to that heat, the shunt motor will get burned. Okay, so option D, that is burned due to heat produced in the field winding. Burn due to heat produced in the field winding will be the answer for this. So what will happen if DC shunt motor is connected across the AC supply? It will burn due to heat produced in the field winding is the answer over here. Clear? Then we'll go to the next question, question number 171. What will happen with increase in speed of a DC motor? Okay, so whenever the speed of a DC motor increases, its back EMF, that is the induced EMF which is there, it will increase, and the armature current, that is line current, falls down because you have to maintain the power constant. So there back EMF increases and the armature line current falls. So here option A is the right answer, that is back EMF increases but line current falls. Okay, so here you can see the explanation. In case of DC motor, the speed is proportional to the back EMF. Okay, so back EMF and speed, you can see EA is proportional to N. So with the increase in speed, the back EMF also increases, but this will decrease the armature current or the line current. Okay, so with the increase in speed, back EMF will increase, but the line current or armature current will decrease. So the first option is the right answer here. Then we'll go to the next question. Question number 172. Which part will surely tell that a given motor is DC motor and not an AC type? Okay. So if you see the outer look of a motor, okay, so there you can see a main part of DC motor as commutator, which is not there in AC. Okay. So that a commutator will differentiate DC motor and not an AC type. Okay. So here you can see all other parts except brushes and commutator are same in AC machine when the outer looks are only taken into consideration. But the a commutator is used only in DC machine for providing mechanical rectification and it is not there in AC machine. So the a commutator will tell you from an outer look that it is a DC machine and not a AC machine. So here the answer should be option C, a commutator. Then we'll go to the next question, question number 173. In DC motor, which of the following part can sustain the maximum temperature rise? Okay. Now, DC motor has a field winding, which is constant, which is not moving, which is stationary, and a armature winding, where the armature is going to have a movement. Okay. So here, the field winding, which is not going to rotate, it can sustain a maximum temperature even when the armature is giving you a rotation. Okay, so field winding is one in DC motor which can sustain maximum temperature. So the explanation is like this: maximum temperature rise can be sustained by field winding as it is not involved in rotary parts, because rotary parts are attached with your armature windings. Okay, Field winding is present away from the rotary parts of the machine. Clear? That is why it can sustain maximum temperature. So here the answer will be option A, field winding. Then we'll go to the next question. Question number 174. A direction of rotation of motor is determined by what? Okay. So whenever a current carrying conductor is placed in a magnetic field, it will it will experience a force, and that force will make it to rotate. Okay. And this law is given by Fleming's law. So Fleming's left hand rule will give the direction of rotation of motor. Okay. So Fleming's laws can be summarized as whenever a current carrying conductor comes under a magnetic field, there will be a force acting on the conductor. And on the other hand, if a conductor is forcefully brought under a magnetic field, there will be induced current in that conductor. So these considerations come under Fleming's law. So Fleming's left hand rule will decide the direction of rotation of motor. A direction of rotation of motor. So option D is the right answer over here. Then we'll go to the next question. Question number 175. The current drawn by the armature of DC motor is directly proportional to what? Okay, so the current drawn by armature of DC motor is directly proportional to the bending moment, the force which is going to bend. Okay, so that bending moment force is called as torque. So A, torque is the answer. The current drawn by the armature of DC motor is directly proportional to the torque. So here you can see the explanation. From the equation of torque generated in a DC machine, we know that in both DC motor and DC generator, a current drawn is directly proportional to the torque required by the machine. A torque is your bending moment. Okay, so a bending moment is called as torque, and your DC current drawn will be proportional to the torque. So here option A, torque, will be the right answer. Then we'll go to the next question. Question number 176. Which of the following quantity will decrease if supply voltage increases? Okay. So if supply voltage increases, then the quantity which will decrease is full load current. Okay, because if supply voltage increases, the full load current has to come down because the power has to be maintained constant. So here option C will be the right answer. So for that you can have an explanation. When supply voltage is increased, full load current will decrease in order to keep output power constant. So V into I, if you take a general statement also, if V increases, then I has to decrease if you want to keep P as constant. Okay, which will decrease the torque at that moment. But the starting torque will remain same irrespective of any change in supply voltage. Okay, then here we'll see that option C, that is full load current, is the right option. So when you decrease the supply voltage, okay, so when you increase the supply voltage, the full load current will decrease. Okay, then we'll go to the next question. Question number 177. Sometimes motor has to be derated. This statement is true because what will happen is a derating refers to the operation of equipment at a reduced capacity per power or speed. Okay, sometimes the motor will give you reduced capacity. No, derating in motors can be caused due to the following reasons. It can be a change in frequency, it can be a change in voltage, it can be a change in ambient or temperature, it can be an altitude problem. Okay, so because of these reasons, a motor can give you a reduced capacity for the same power or speed. Okay, so that is called as derating. So derating can happen in a motor. So this statement is true. Sometimes motor has to be derated. It is true. Okay, then we'll go to the next question. Question number 178. The armature torque of a DC motor is a function of what? Option A says field flux alone. Option B says armature current alone. Option C says speed alone. And option D says both field flux and armature current. Okay. So the armature torque means the bending moment. The armature torque of a DC movement, of a DC motor, okay, will depend on the field flux and also on the armature current, because field flux also is the flux which will make the rotating part to experience a force. So the armature current that is going to be placed in the field flux, okay, and that is where it will experience a force, because its own magnetic field will interact with the field flux, and then it will start moving, it will start rotating, there will be a torque. Okay, that means both field flux and armature current are responsible for armature torque of a DC motor. Okay, so option D will be the right answer here, both field flux and armature current. Then we'll go to the next question. A DC motor is used in industrial application because. So the options are: it is cheap. Option 2 is it is simple in a construction. Option 3 is it provides fine speed control. And option D is none of the above. The best advantage of DC motor to be used in industrial application is because it provides very fine speed control, very minor speed control also you can have. You can have SCR circuits, you can control the firing of SCR with electronic circuits, and with those you can control the speed of DC motor. Okay, so the option C, provide fine speed control, is the right answer for this question. So option C, a DC motor is used in industrial application because it provides fine speed control. Speed variation can be controlled very finely at a very low speed also, or at a higher speed also, very accurately you can control the speed of the motor. Okay. Then we'll go to the next question, question number 180. The field poles and armature of a DC machine are laminated because for what? Option A says reduce the weight of the machine. Option B says decrease the speed. Option C says reduce eddy current. And option D says reduce armature reaction. Now, this type of lamination theory we have also seen in transformer course. Okay, so laminations of the armature or the field poles is done mainly to reduce eddy current. So the induced current, whatever will be there because of magnetic induction, that has to be reduced. So here option C will be the right answer, reduce eddy currents. So the field poles and armature of a DC machine are laminated to reduce eddy currents. Okay. So students, these were another 20 questions which I have taken on BEEE DCT. Uh, in my next video, I will take another 20 questions on the next topic of the same subject. Thank you very much.